Hypothesis testing. This is another way to do statistical inference. The first way we looked at was point estimation, then interval estimation. We spent quite a bit of time with interval estimation, but now we're going to focus on hypothesis testing. All right, let me first talk about what a hypothesis is. So a hypothesis for us is a statement about one or more populations, usually concerned with the value of a parameter. Okay, this numerical description of the population, we want to say something about it. So for example, a hospital administrator may hypothesize that the average length of stay, in this case the average here is the parameter mu, but he may have hypothesized that the average length of stay for admitted patients is 5 days. So his statement is that mu is equal to 5. All right, and in a hypothesis testing, we want to say something about such statements. Are they believable? Should we outright reject them? What does the evidence from the data suggest about such statements? That's what hypothesis test does for us. Okay, first here, a term or a phrase here, research hypothesis. This is the conjecture that motivates the research. Okay, so most scientists have a research hypothesis. They think that a particular phenomenon behaves a certain way, and that ultimately motivates the research. And oftentimes, a research hypothesis can be formulated into a statistical hypothesis. That's a hypothesis that's stated in a form which may be evaluated by appropriate statistical techniques. And here we have two competing hypotheses. Okay, one is called the null hypothesis, and the other is called the alternative hypothesis. All right, so I wanted to kind of take an aside here to the criminal courtroom. Look at a courtroom example thinking about the null and alternative hypotheses. Now, the null hypothesis is initially assumed true. Now, in the courtroom setting, the thing that's initially assumed true is that the defendant is innocent. Okay, in the American legal system, that is the starting place regarding the defendant's guilt or innocence, innocent until proven guilty. That's initially assumed true, okay, regardless of the evidence. Now, the prosecutor defends the evidence and a jury makes a decision. The prosecutor wants to arrive at the alternative hypothesis, which we highlight or designate as H1 here, and that's that the defendant, let me make that the defendant ditto marks is guilty or is not innocent. Okay. And in the courtroom, the prosecutor must provide overwhelming evidence. In fact, we have a phrase for this: beyond a reasonable doubt. To reject the null and accept the alternative. That is to reject the idea that the defendant is innocent and accept the alternative that the defendant is in fact guilty. Okay. The approach is the same as statistical hypothesis testing, except our evidence is statistical. Okay, so as opposed to fingerprints, DNA evidence, this sort of thing, our evidence is statistical. It is strictly from data. So using the data, we want to say something about hypotheses, the null and alternative hypotheses regarding the parameter of interest. Now, in hypothesis testing, we have types of errors. We don't know the truth. Just like the courtroom setting, unless the defendant um, uh, comes clean, if he or she is actually guilty, or somehow the truth is found out. Oftentimes the truth is not known, but a decision is made from the jury. The same, it's that way in hypothesis testing. We don't know the value of the parameter, but we make a decision about statements regarding that parameter. Okay, so there's errors involved, and there's two kinds of errors. Okay, so if we want to think about if you want to think about this in terms of the courtroom setting, again, we can if we want to. But this table here is a nice summary, or a nice way to look at the kinds of errors that can occur in hypothesis testing. So in hypothesis testing, we have the truth here. I've got a little 2x2 table here. The columns are labeled H naught is true versus and H naught is false. Those are the two options there for the truth. And the rows correspond to the decision that is made by the researcher. That is, H naught is true or H naught is false. Okay, and so based on those two sets, the state of truth and also the choices that are made, there's four possibilities here. And so this first possibility here, if the null hypothesis is in fact true and the decision is to assume it's true or to state that it's true, we have failed to reject the null hypothesis, and in this case we have made no error. Okay. All right. In a similar way, in this 2-2 entry of the table, if the truth is the H naught is false, but we reject H naught and we decide that H naught is false and accept the alternative, then we have made no error. Okay, so there's no error in those two situations, in the 1-1 and then in the 2-2 entry. On the other hand, in this 1-2 in the 1-2 entry here, actually let's go with the 2-1 entry in the lower left hand part of the box. If H naught is true, but you decide to reject H naught, then you have rejected a true null hypothesis. And in doing so, you have made a type 1 error. Okay. Statisticians call this a type 1 error. That is rejecting a true null hypothesis. If it's true, you don't want to reject it, so you made an error. On the other hand, in this upper right hand part of the box, if the truth is that H naught is false, but we fail to reject it, then we've made what's called a type 2 error. Okay, and this error is failing to reject a false null hypothesis. And clearly, if something is false, you would like to reject it, so that's an error. That's a type 2 error. All right, both errors are bad. You don't want to make either one of them. But we have to be mindful that both of them could be made. Now, the probability of a type 1 error is set at a value alpha, which is the significance level of the test, and we'll define that in a little bit. And the probability of a type 2 error is set at beta. Now, it turns out that alpha and beta are inversely related. So I'll write that down here just so you'll have a note of it. Alpha and beta, that is, sometimes we say the type 1 error rate and the type 2 error rate, they are inversely related. What I mean by that is, all things considered fixed and the same, if you force alpha to go up, beta will go down. If you force alpha to go down, beta will go up. Okay, so they have this inverse relationship. So you can't you can't have these be really close to zero all the time for any situation you want. It depends on other factors, but generally speaking, alpha and beta are inversely related. And so what's done in hypothesis testing is we fix the alpha to be a certain value, and then we have a hypothesis test scenario or scheme or method, and we look at how the method performs for different values under the alternative space or under the alternative hypothesis, and that will give us a sense of the type 2 error. Okay. A little more about these hypotheses. One, the null hypothesis. Well, this is the hypothesis that's being tested, and we assume throughout the hypothesis that this is true, that the null hypothesis is true. The null hypothesis is the opposite of the conclusion the researcher is trying to support. Okay. Now, one thing about the null hypothesis, we either choose to reject it or we fail to reject it. We should not accept it. Okay. Notice, I'm going to write the word accept here. We should not accept the null hypothesis. Saying accept the null hypothesis is a stronger statement than failing to reject the null hypothesis. Right? Fail to reject H naught is weak compared to let's accept the null. All right. I had a former student that aptly said, in terms of the statements that we can say regarding H naught, it's easier to know what's not true than what is true. And I thought that was a pretty clever statement. And so that's kind of the philosophy behind our statements regarding reject H naught or fail to reject H naught. Okay. Now, the alternative hypothesis, HA or H1 as it is sometimes written down as, I think on the previous page I have H1, but you may see HA, H1 in several different contexts. It usually corresponds to what the researcher is trying to support. Let's see here. Or the research hypothesis being tested, or the claim. I need to back up. It corresponds to what the researcher is trying to support or the claim being tested. Okay, so at the very beginning here we had a claim that a hospital administrator said that the average length of stay for admitted patients is 5 days. We could test that claim. All right, that sort of thing. All right, so let's go back down here. We have the null and alternative hypothesis. Now, some types of hypothesis tests for a population mean. With this module, this chapter, we are looking at doing statistical inference on a population mean. We had looked at confidence intervals on a population mean. Now we're moving to hypothesis test on a population mean. We have several different kinds of test. We could, I'm going to first off start off here by saying that I'm going to fix mu naught. I'm going to say mu naught is a fixed number. So it could be, say the number 3. And I could test that mu is less than 3. Well, if that's the claim I want to test, then I'm dealing with this kind of alternative hypothesis in what's called a left-tailed test. And if that's a statement I want to test, that mu is less than 3, that would be a left-tailed test. Notice the null hypothesis then becomes that mu is greater than or equal to 3, or mu naught here. All right. If I want to test if mu is greater than 3, I would have an alternative that looks like this. And this would be a right tail test, and my null hypothesis would be that mu is less than or equal to 3. On the other hand, I could test maybe not a particular direction, but just that mu is not equal to 3. Okay, so that would be the alternative, that mu is not equal to some value. The null then would be that mu is equal to that value 3, and this is called a two-tailed test. Okay, so we have these kinds of hypothesis tests for a population mean. Moving along here, some more terms within hypothesis testing. One is called this significance level, and it is the probability that we reject a true null hypothesis. In other words, the probability of a type 1 error. Now this value is denoted by alpha, and it's set by the researcher. We usually have values 1%, 5%, 10%, this sort of thing. You want this to be pretty low, not much more greater than 10%. If the type 1 error rate is a severe or has a severe consequence, a really severe consequence, then you may want alpha to be really low. If the type 2 error rate is more severe, and the type 1 error is not that severe, then you may set your alpha a little bit higher, closer to 10%. But typically values of 1, 5, or 10% are chosen for a significance level. The power of a hypothesis test is the probability of rejecting a false null hypothesis. And the power of the test is 1 minus beta. Recall, beta is the probability of a type 2 error. So using the complement rule, the power of the test is 1 minus beta. Now you want the power of your test to be high. Ideally that is a high quantity. It turns out the power of the test, and you'll see this in your text and as you work through problems, is a function of the true value of the parameter. And as that true value of the parameter gets away from the null hypothesis, you'll see that the power of the test will go up. Okay, this is another quantity we're interested in. The assumptions of a hypothesis or of a test statistic. These are properties that must be satisfied so that the test statistic will have the assumed probability distribution that we are making, and that the test statistic will be valid for the given data. So we make assumptions about our test statistic. We had this sort of thing in our confidence interval situation where we made assumptions in order to use a particular confidence interval formula. Now, what is a test statistic? So I kind of got ahead of myself here. What is a test statistic? Well, it's a quantity computed from the sample, and it's used to make a decision in a test of hypotheses. Okay, the test statistic is always computed under the assumption that the null hypothesis is true, and the test statistic is our evidence. Our test statistic singular is our evidence. I must have missed that. The test statistic is our evidence from the data. And this evidence is always against the null hypothesis. Okay. The general form of our test statistic is the relevant statistic. So for example, X bar might be here, but it's our relevant statistic minus the hypothesized value, the null hypothesized value, divided by the standard error. And that form is what we're going to use for most of our test statistics in this class. And in some sense, it's a distance measure between what the data says about the parameter and what the null hypothesis says about the parameter. And we measure that distance on a probability distribution, such as the normal distribution or the t-distribution. And we'll see that fleshed out in some examples. Rejection region is the values of the test statistic that provide strong evidence against the null hypothesis in favor of the alternative hypothesis. Okay? It's where you reject the null. You say, if my test statistic falls in this region, I'm going to reject the null. That's why it's called the rejection region. But I'm going to reject the null and accept the alternative. Now, this region is chosen by the researcher in such a way that the evidence is sufficiently strong. It's going to be hard for the test statistic to fall in the rejection region, or it's going to be very unlikely for the test statistic to fall in the rejection region if in fact the null hypothesis is true. So if we see that our test statistic fell in this region, we've seen an unlikely event, so our evidence is very strong towards the alternative hypothesis and against the null hypothesis. Another term here is called the p-value. This is the probability of getting a value of the test statistic as extreme or more extreme than what you observed from your sample, assuming the null hypothesis is true. The p-value, if the p-value is very small, then we have observed an unlikely event. Okay, an event so unlikely we must reject the assumption that H0 is true. Okay, this is going to give us a gauge on how we make a decision about our hypothesis test. All right, the p-value. The p-value is computed differently depending upon the kind of test. If we have a left-tailed test, then the p-value is the probability of seeing another test statistic less than or equal to what we observed from our sample. That's the left-tailed test. If we're in a right-tailed test situation, then the p-value is computed as follows here. The chance of seeing a test statistic more than or equal to the observed test statistic value. If we are in a two-tailed test situation, then we've got our probability our p-value is 2 times the probability of seeing a test statistic bigger than or equal to the absolute value of our observed test statistic. Okay, and as you work through more examples of hypothesis tests, you should become more comfortable with computing these different kinds of p-values. All right. Now, all that said, what are the steps for a hypothesis test? It would look something like this. And we're going to work most of our hypothesis test problems through this 5-step procedure. It's a nice way to organize ourselves when doing a hypothesis test. The more hypothesis tests you do, the more comfortable you get. You don't necessarily have to do all these tests unless I ask you to do that, but you don't necessarily have to do all these tests in order to make a decision about the hypotheses of interest. But the 5 steps look like this. Number one is you first define the parameter of interest. What is this single quantity from the population that we want to say something about? So you define your parameter, then you set up the null and alternative hypotheses. Step 2, you state the test statistic that you're going to use and its distribution. We have a special term for this distribution. This distribution is usually called the null distribution. It's the distribution of your test statistic assuming the null hypothesis is true. Step 3 here, you select a significance level, that's an alpha, and specify the rejection region and or the decision rule. Now, the decision rule tells us when to reject H0 and when to fail to reject H0. It just puts into words the picture of the rejection region. Step 4 here, we check the assumptions. calculate descriptive statistics, and compute the value of our test statistic. So our test statistic will have certain assumptions in regarding to that will affect its validity. We need to check those assumptions from the data, calculate descriptive statistics from the data, and then ultimately compute an observed value of our test statistic from the data. And once we have all that, we can make a decision. Now there's two ways to make a decision. The first way is ask yourself the question, does the test statistic lie in the rejection region? And if the test statistic does lie or fall in the rejection region, then we reject H0 and accept HA, the alternative hypothesis. Let me use H1. I think I'll use H1 there. If the test statistic does not fall in the rejection region, we fail to reject the null hypothesis. The second way of making a decision is as follows. If the p-value is less than alpha, then we reject H0 and accept the alternative. If the p-value is bigger than or equal to alpha, we fail to reject the null hypothesis. Now both methods above lead to the same decision. And we'll kind of see this fleshed out in a picture in an example later on. But you can use the p-value and compare it to alpha to make a decision, or you can ask the question, does my test statistic fall in the rejection region, to make a decision. Both will lead to the same result, the same decision here. Okay, so that's kind of a lengthy video that describes, but there's a lot to describe here in the foundations for hypothesis testing. Next video we'll look at a particular case doing a hypothesis test for mu when sigma is known.